in this video we are going to discuss about the scaling of the MOS transistor. So on completion of this topic, the students will be able to understand what is the basic idea behind the scaling of the MOSFET, and also what are the best ways we can use to increase the performance of the MOSFET transistor. So why scaling? So why scaling means, this scaling of the MOS transistor means reducing the critical parameter of the device in accordance with the given criteria in order to improve some performance features such as speed, application, power dissipation, and also keeping the basic operational characteristics unchanged. So this is why we are going for the scaling, and here this design of the high density chips in the MOS VLSI technology requires high packing density of MOSFETs, small transistor size. So this reduction of the size is scaling. And also here we can say the advantages of the scaling in the MOSFET is packaging density. So this packaging density of the device that is improves as a result of the scaling can fit more than the transistor in a small space, or we can say it is in a little area. So in the chips, size of the chip means as we can pack more number of transistors in the small space, this can decrease the overall area of the chip. And in the case of multifunctioning of the chip, as the transistor size is reduced, we can make multifunctional chips by decreasing the area of the chips. So based on the three defined things, that is packaging density, size, chip size, and multifunction of the chip, this is the advantages of the scaling that requires a less area with more applications. So here the disadvantages: electric fields within the gate oxide grow larger. So types of scaling. So in the case of types of scaling, first one is constant field scaling or full scaling. So in this, all the parameters of the MOSFET is scaled to understand, and its better way we will be considering a case that suppose this scaling transistor is S, and also if this value is greater than 1, here we will consider all the parameters of the MOSFET can be scaled by the scaling factor S, then its all parameter will get changed to a new value. So for example, if the original gate length is L, then after scaling it will become L dash is equal to L by S. So in a similar way, all the parameters of the MOSFET will get changed to their new value. Hence this type of scaling is known as full scaling. So you can see the consequence of this constant field scaling: channel length before scaling and after scaling, channel width, gate oxide thickness, junction depth, power supply voltage, threshold voltage, doping densities. So you can see before scaling what happens and after scaling what it happens. So most significant reduction is power dissipation is reduced by the factor of S square, as P dash is equal to P by S square. So this power density remains unchanged, and gate oxide capacitance is scaled down, Cg dash equal to C by S, and overall performance is improved. And second one is constant voltage scaling. So in this only the physical parameters of the MOSFET are scaled down, so such that the gate length of the MOSFET is decreased, and this results in the short channel effect, so which is directly affecting the drain current, and also this drain current is inversely proportional to the gate length. So here the electrical properties are kept constant, and also this terminal voltage is also kept constant. So here you can see the dimensions, the voltages, doping densities before and after scaling, and the quantity of oxide capacitance, drain current, power dissipation, and the power dissipation before scaling and after scaling. And in the increase in the drain current density and power density by a factor, it is affecting the device mobility, and also it causes certain problems like electro migration, hot carrier degradation, gate oxide breakdown, and electrical oversteer. So short channel effects: when channel length approximately equals the source and the junction depth, why the short channel is even degrading its performance, and why this voltage is less means it causes due to the effects of drain induced barrier lowering, surface scattering, velocity saturation, impact ionization, and hot carrier effect. In the case of drain induced barrier lowering, this potential barrier is controlled by both the VGS and the VDS, and also if its drain voltage voltage increases, barrier in the channel decreases, leading to this drain induced barrier lowering. This allows the electrons flow between the source and the drain. In the case of surface scattering, due to the surface scattering, this electric field increases and the mobility becomes field dependent, and the surface scattering occurs, also this average mobility decreases. In the case of velocity saturation, this velocity of the charge carriers is this versus the electric field. So it operates in the three regions. So in this three regions, it reduces the current in the short channel effect, and this formula is IDS long divided by 1 plus E by EC. In the case of the impact ionization, here when this current, that is gate current, is produced to this electron starts moving from this mobilization from one part to another. So when this channel, when high electric field is produced, this causes high velocity of electrons, which occurs in the form of electron and hole pairs. Next one is Hart carrier effects. So in this Hart carrier effects, when electrons or holes are having more energies to overcome this barrier, this permanently changes the MOSFET switching characteristics, and also it occurs in a reliable way. So that is when source and drain is present, and this gate is, when electrons are moved towards the gate oxide, this can cause some electron holes carrier, which can overcome this barrier to a electron potential, and also it can permanently changes to the switching characteristics, which causes reliability. Quiz questions on the introduction to scaling. First one, as load capacitance of logic current will increase, dynamic power will decrease, increase, constant, or no change. Thank you.